Good morning, students. So today we will be studying about Bode plot. Firstly, the Bode plots are one of the methods of frequency response. As we have already studied that in frequency response, we always plot two curves. One is with respect to frequency, magnitude versus frequency, and the second one is phase angle with respect to frequency. So in this, both of the graphs, that is gain versus omega and phase angle versus omega, are plotted on the same semi-log paper. So here we are going to use semi-log paper, while the frequency is always plotted on the logarithmic scale. So the advantages of Bode plot, that is very important and comes in the examinations also. So the main one is that multiplication gets converted into addition. You all have studied about logarithm. So you all know that if we have a function gs equals to k divided by s multiplied by 1 plus st, then you know that the division sign always gets converted into subtraction, while the multiplication sign gets converted into addition. So you can see the equation that is given below, that becomes 20 log k, that is the numerator part, minus 20 log j omega minus 20 log 1 plus j omega t. So both low and high frequency characteristics can be represented on a single diagram, because semi-log paper can show a wide range of frequency and gains into a viewable whole, into a single graph paper. Study of relative stability is easier, as gain margin and phase margin that we are going to study when we are going to solve our numericals are all visible on a single semi-log paper. Plotting of Bode plot is relatively easier, as loci of different functions are represented by straight line asymptotes. So some definitions of logarithmic terms. The first one is that vertical axis is scaled using decibel. So we must know the meaning of decibel. You all know that it is used to measure power. So power gain will be equal to output power to input power. So when we talk about bell, it becomes log to the base 10 of P naught upon Pi. So here P naught stands for the output power and Pi for the input power. But when you talk about decibel, your this thing gets multiplied with 10 and it becomes 10 log to the base 10 P naught by Pi. So that means 1 decibel is equals to 1 by 10th of a bell. Okay. So now you know that power is equals to V square divided by R. So when you are going to put B into equation A, you are going to get gain equals to 20 log of V naught by Vi. So that is always plotted on the vertical axis. This 20 log V naught by Vi we are going to plot on the vertical axis. So next on the horizontal axis, I already told you that we plot omega, but the terms that we used to plot the slope of the Bode plot, that is vertical axis versus x-axis, we always plot in either the slopes are plotted per octave or per decade. So there are two terms, octave and decade. So let's learn about them. Octave is used to express frequency band or ratios from f1 to f2. If we are going to measure the ratio, we are going to take the ratio between two frequencies, that is f2 divided by f1, and the ratio comes out to be 2, then that becomes a octave. For example, if f1 is 17.4 Hz while f2 is 34.8 Hz, then they are 1 octave apart in width. Similarly, 1 Hz and 2 Hz are also 1 octave apart. So doubling of frequency is called 1 octave. As the number doubles, the decibel value, mind it, the decibel value increases by only 6 decibels. So decibel value of f2 in above examples is 6 decibel greater than f1. Now we come on to decade, that we are going to use to plot our Bode plot throughout our this session, because we are going to solve the numericals using per decade slope, not per octave. So basically decade is used to express frequency band or ratios from f1 to f2 when f2 by f1 ratio is equals to 10. So for example, if f1 is 2.5 Hz and f2 is 25 Hz, then they are 1 decade in width. Similarly, if f1 is 1 Hz and f2 is 10 Hz, they are also 1 decade in width. But as the number increases by a factor of 10, the decibel value increases by 20 decibel. Like an octave, it was only 6 decibels, but here it is 20 decibel. So the 100 Hz frequency is 10 times larger than the 10 hertz frequency, and its decibel value is 20 decibel greater. So now we come on to the semi-log paper introduction. As I already told you that x-axis is spaced logarithmically, while the vertical axis is linearly spaced in equal intervals that we have normally seen till now in our graph papers that we use to plot the various graphs in our different classes. There is a difference between log and semi-log graph paper. Why I am telling you is this, because when you go to the stationery shops and you ask for the semi-log paper, they sometimes provide you with the log paper. So you should learn the difference between the two. Just check the two here. The left one is the semi-log paper while the right one is the log paper, and just check the x-axis and the y-axis. If you check the semi-log paper, only one axis is logarithmic, while the second here the x-axis is uniformly spaced. So equal intervals are there on one axis, but when you see the log graph, you are going to see that both x-axis as well as the y-axis are logarithmically spaced. There is uneven distribution in the two axes. So always beware when you are going to buy the semi-log paper from a stationery shop, it should be like the left one. So basically when you are going to buy the semi-log paper, it comes in mostly 5 cycle semi-log paper come, and they are used where one cycle consists of 9 spacings. You can see that one cycle here I have taken 3 cycles. So first cycle covers 1 to 10, then second cycle covers 10 to 100, then third cycle is 100 to 1000 and so on. So you can see that 5 cycle graph semi-log paper is going to cover up till 10 raised to the power of 5. So now you can see that there are 9 spacings and they are all unequal. Now we are going to give the markings to all of these. So this is how your semi-log paper is going to look. Now just see here that just a second. You have to just see here that why these markings on logarithmic scale are uneven. To know the answer, you just check out this table. You can just see that the difference between 10 to 20 is 0.3. Just check, log 10 is 1 while log 20 is 1.3. So the difference is 0.3. While when you go from 20 to 30, 1.48 minus 1.3, the difference is only of 0.18. So that is why the uneven difference is there in the x-axis on which we are going to plot the omega, because there is uneven increase between when you go from one number to another number. So now you can just check out that how we are going to give the markings on the x-axis. Basically when you are going to buy the semi-log paper, it is already marked like the given in this above one, the above numbers 1 2 3 4 5 6 7 8 9, then again it starts from 1 2 3 4. So it starts from here, and how you number it, just check the downward line where the numerals have been written. So you go from right from 1 to 10, then the next number becomes the multiplier of then 10. All the numbers in the second cycle becomes the multipliers of 10. So that becomes 10, 20, 30, 40 up till 100. Now the next cycle will be a multiple of 100 now. So the first number will be 100, then 200, then 300, then 1000. Now the next cycle, that will be the fourth one, will be a multiple of 1000. So these are some commonly used values of decibel that you require for solving your numericals. Now when we are going to plot our magnitude plot, it will be somewhat like this, and main thing that you should remember is the baseline that is taken to plot the magnitude curve is always the 0 dB axis. Here the 0 that is shown shows you that it is 0 dB, and above 0 dB we always plot the positive values, while below it we plot the negative values. Similarly for the phase plot, the baseline is always minus 180 degrees. So this you should all remember. and these two plots, they both are plotted on the same semi-log paper. Yeah, that means when you are going to solve the numerical in your exams, you will be given with a single semi-log paper and you are going to plot both magnitude as well as phase plot on the single semi-log paper. So now we come on to the important tables for drawing the Bode plot, and you are going to note them down in your notebooks, because before the next lecture I'm going to put, you should all be familiar with these two tables. The second one I am going to go for the detail in the second lecture of the Bode plot, while this will be required when we are going to plot our first numerical. So here you only need to know that your intersection with 0 dB axis is k raised to the power of 1 by n, and it directly depends on the type of the system. As the type of the system increases, so is the value of k raised to the power of 1 by n. That is, the root of k keeps on increases. This is the second table. You only need to write it down right now, because these are the various function of a transfer function that we are going to plot using Bode plot. Nothing to worry about, because in the second lecture that I am going to attach after this lecture, you are going to understand each and every single term and how we have drawn this table. So this is basically a summary of the Bode plot, magnitude and phase plots that we are going to need. So that's all for now. Thanks for watching.